Welcome back to the lab. Alright. Okay. I admit defeat. I give up. I concede. We will never get this design to withstand a 40-volt input. We'll never get our UPS design to withstand a 24-volt DC input. Fine. Thankfully, I got a high current 12-volt supply for a couple bucks on Amazon, so let's push this design as far as we can. We've learned a lot from this UPS with our low power, current limited testing, and I imagine there are a couple more lessons to learn hidden in here somewhere. This design may not meet all of our requirements, but I want to learn everything there's left to learn from this design before we move on and spend more time and money making a new prototype. Are you ready? Buckle up. It's time to take things up a notch. We have 3 phases of testing to run through. No load tests, light load tests, and medium load tests. Actually, the test procedure is just the same and repeated 3 times, 1 for each load level. And we get a little lazy and skip a couple steps towards the end, but that's okay. We start by checking for current symmetry. This is verified by monitoring the I feedback net, the current feedback voltage net. We tried probing near the current sense resistor before, but that wasn't working too well for us, so let's try using the buffered version of this signal near the controller IC further away from the currents. So this is what we're seeing on the voltage monitoring node. If we're to believe the peak to peak, that'd give us almost 2 volts. Almost 2 volts. If we're saying that's noise and we go down to what we're seeing down here, we would be seeing saying 120, 200 millivolts. So here's the thing. There's still way too much noise. Like, I can see a waveform that looks approximately symmetrical, which is good. However, I can't see much else. There's just so much noise on the current monitoring nodes. It's really difficult to make a conclusion. I'll leave this as a tentative, it's probably fine. But I really just don't know if I'm going to be able to see what I want to see here. What's next? We need to measure the peak voltage applied across the drain and source of the transistors. Now this is to verify that we aren't in danger of blowing things up. Sorry, 200 volts is our VDS limit. That's the top cursor set at. Bottom one set for 150 just for reference. Alright. First, turn on. This is no load. Right. Like we've mentioned before, the VDS stress is higher than ideal with this snubber. We're hanging right around the 175, 180 volt range, which provides about 25 volts of margin on the 200 volt rating of the FETs. With varying load level, this changes a bit, but we never get too close. Okay, we get pretty close to 200 volts. It's not great, but it's acceptable. At least they haven't blown up yet. I wouldn't want to leave it like this way as a long-term solution, but it's fine for a little bit of testing. Our next measurement is voltage ripple on the DC bus feeding the FETs. Large dips here would indicate spikes of power dissipation that we may not expect, or high ESR on our input caps that need to get fixed. DC drops might also indicate resistive losses in other circuits on the PCB or the PCB itself. I'm seeing about 7.5 volts of ripple on the DC input when operating at pretty light load. Can anyone say insufficient bulk? I think we need more caps or capacitors with lower ESR, so dang. Perhaps we'll uncover something more as load level increases, but man, this looks pretty bad already. Our last sanity check is the gate drive signal amplitude. Let's make sure that we never violate the 20 volt VGS, or voltage gate to source rating. One quick measurement later, and as expected, it's limited to 10 volts, which makes sense because that's set by the fan supply voltage. What's next? Let's load our inverter and run these tests again. We're targeting 60 watts on the kilowatt meter, so let's grab some light bulbs, resistors, whatever it takes to get this thing loaded properly. All right, 60 watts, let's roll. Rinse and repeat. First, we want to look at that current symmetry again. Still noisy, still inconclusive, difficult to say. Now, the peak VDS stress actually dropped down a bit. We're hanging around 100 volts now. Not bad. DC input ripple, yeah, went up a bit. About 8.5 volt peak to peak voltage ripple on a 12 volt input. Moving on. Gate drive amplitude, still solid, still 10 volts. So cranking this up to 200 volts, this is where things started getting a little explodey melty last time. Now that's a technical term. Did our snubber fix the problem? Are we ready for this kind of power? Come on, baby, I need a win today. Let's start with peak VDS stress because I'm a wimp. Because I'm cautious. Looks like we're back up to... Oh. Yeah, looks like we didn't quite get to 200 watts.
Yeah, DC bus is not getting up to the voltage we would expect. We are dropping a ton of voltage. What is up? There's only one thing that I can think of, and that would be if the input voltage is failing, and so will the output. Whoa! That was in current mode. Alright, let's try that in voltage mode. There we go. Start up at like 200 volts. Let's try this again. Hey, voltage regulation is a thing. Our bulb is bright. And let's look at what our DC input is. What the heck? At 11.5 volts in. This converter is weak. Well, we're doing better than we did last time. Yeah, so we're up at 12.6, and hopefully the thing doesn't explode. Oh, wow, that was a relief. Looks like not only does the converter not pump out can't handle the voltage we need on the input, it also can't operate at the high power that we need at the low input voltage. Because this supply is capable of like 20-30 amps. We should be able to get at least 100 watts out. But the DC bus voltage is sagging from 250 volts down to nothing before we even get there. We can't even finish our load test. Where's my spreadsheet? But we're supposed to push this thing up to, you know, like 300-400 watts for the full load, or so it'd be like a half load test. We're supposed to do like a half load test with this thing, and the DC bus is gonna crap out before we even get there. Not great. Not great.
I know, every time I turn up the voltage something blows up, and we just talked about that, but I can't help myself. I want to get 200 watts out of this UPS. So with the input voltage set to around 12.2 volts, nothing is blowing up, and the DC bus drops from 250 volts down to around 130, but we're still able to hit 120 volts RMS on the output with an 87 watt load, probably with a bit of clipping, but whatever. Now, this is a huge hint to me. This gives me an absolutely great idea of what's going wrong. Our leakage inductance is probably too large. Not only is our leakage inductance too large, our leakage inductance is large enough that with this power level, voltage regulation fails. The ideal push-pull equation breaks down. Well, either that or we're starting to saturate the core. That second one would really surprise me because this thing was designed for 700 watts. Remember, we're only at a couple hundred. So my bet's on that leakage inductance. There's a couple winding strategies that I think we can use to minimize leakage inductance moving forward, but they typically come along with some compromises with regard to isolation, and I think that by using a dielectric spacer around the core, like a Kapton tape, to distribute the primary winding across the secondary, instead of 3 horizontal slices next to each other, I think we can get this closer to where we need to be. It's definitely something we should remember for the next prototype transformer we make, and could save us quite a lot of time. Why are you looking at me like that? Oh, tangents.
Full load.
Whoa. Yep, that's some clamping from our bus. That's extra power dissipation in our FETs. That's not what you want. It's not enough to blow them up apparently, but oh boy, that does not look great. So, about current symmetry. My measurements are all incredibly noisy. Oh, that changes a lot when we had the heavy load. Okay. Not really sure what to make of that. That's weird. That's the current monitor. Perhaps I need a different, better analog ground probe location planned for the board, like A ground and P ground. This is just nuts. Using power ground as a reference for millivolt level signals does not appear to be the best approach. Gonna have to keep that in mind next time. DC input ripple. The DC voltage ripple is 16 volts. What? Literally larger than the input voltage. Okay, yeah. Improvement required. Got it. Hear it loud and clear. Gate drive amplitude, still great, 10 volts. Now, I just can't help it, and maybe it's just the engineer in me. Maybe it's my constant need to optimize. Maybe I'm just having fun. I don't know. This just isn't good enough for me. It's pretty good. It's just not good enough. I know that I can and I want to do better. I see a few limits of this system right now. Input voltage limited by the push-pull symmetrical power supply topology. Input power and efficiency limited by availability of an appropriate AC to DC power supply. And output power limited by the losses in the output filter inductor. Something tells me it was just never designed for 100 kilohertz. Oh right, the massive wire. That's what it is. Okay then, so how does the efficiency look? AC to DC, control circuit, snubber, filter, AC in, AC out, everything. How are we doing? Well, right now, better than I expected. With 87 watts out, we're drawing 193 watts from the wall. That's a total efficiency of 45%. That might not seem like a big deal. That might not seem very good. But you have to remember that all of our previous efficiency measurements were taken after the AC to DC conversion, so we added another layer of inefficiency here. Odds are that AC to DC supply is only between 80 and 95% efficient, depending on the implementation. So that means that at worst, our DC to DC step-up conversion and inverter output stage are actually pretty efficient. And the control circuitry isn't really a power hog, so wow. Now that I'm thinking about it, this measurement actually didn't remove power consumed by the control circuitry at all. So if I massage these numbers in the same way that we were doing before, removing the 20 watts we dissipated idle, taking out 5% for AC to DC conversion, that brings us to around 53% efficiency. Not bad. We're definitely making an improvement over our previous load testing. Remember, our efficiency started out around 70% and kept sinking like a rock as output power increased. So when we got up to like 40, 50 watts, we were below 40% efficiency. Our UPS is certainly not ideal, but I think that I'm starting to really understand exactly where and why the UPS is misbehaving, and I'm starting to get some pretty good ideas on how to fix it. We learned a lot about the UPS that we designed today, and finally ended a video without destroying a board. Boo, yeah. If you like what you saw today, consider subscribing to be notified of our future videos where we'll test our inverter overcurrent and soft start functions and perform some higher level UPS system tests. I think that our testing today was not perfect, but it was very promising. If you think so too, let me know by hitting the like button on this video or leaving a comment letting us know what's on your mind. Most of all, I hope that you learned something great today, and I hope to see you again soon. Thanks for watching EE for Everyone, and thank you for staying till the end. Bye!